Hello, Mr. Adams and class. I'm going to present to you a tale of two laws, Moore's Law and Amdal's Law. Ever since I was a kid learning about computers, I've known about Moore's Law for pretty much my whole life, and I just wanted to really do a project focused on that, and that is what is the scope of this presentation. Let's start with some quotes from professionals. Computer hardware progress is so fast, no other technology since civilization began has been 6 orders of magnitude in performance price gain in 30 years. This was said by Fred Brooks Jr., an American software engineer. And then computers should be made of glass. They're so full of bottlenecks. And this comes from our own textbook author, Alan Clements, in March of 2001. In giving you a brief history of the two laws, I start in the year 1965, where Moore's Law was propounded by Gordon Moore. He was the co-founder of Intel. And then in 1967, Amdal's Law was first proposed by Gene Amdal, who was an American entrepreneur. And in 1970, the term Moore's Law was coined by Carl Mead, an American scientist. And then, almost just recently, in 1988, John Gustafson of the Sandia National Laboratories in the United States suggested some corrections by reevaluating Amdal's Law. Moore's Law and the March of Progress in Computer Technology. To give you a little information about Moore's Law suggested that there was an exponential increase in the maximum number of components on a chip at a time. Now, Moore's Law is an empirical observation that the number of components on an integrated circuit doubles every year. It is not really a true law based on physics, it's just simply an observation. And now, over time, Moore's Law has been come to imply that there's a doubling in the performance of digital systems every 18 months. There really is no precise formalization of Moore's Law. Now, Moore's Law is based on an observation of the progress of the semiconductor technology, and the trends that Gordon Moore observed in the 1960s have continued largely unbroken until 2010. Now, this is something that is probably unique in human endeavor. If a man in 1960 was sauntering along the street and he increased his speed in accordance with Moore's Law, he would be moving at more than 33 million miles an hour in 2010, which is nearly 10,000 miles a second. And next we will cover Amdal's Law and its infamous governing computer performance. Now, it is infamous law because it appears to place a limit on the maximum performance increase that can be achieved by optimizing a computer subsystem. We are now living in a world where we have parallel computing. And parallel computing is computing more than one value simultaneously. Amdal's Law deals with the potential speed up of a program using multiple processors compared to a single processor. It also describes the performance increase that you get when a program is run in a system where some of the operations can take place in parallel. 3 other facts about Amdal's Law is that it tells you what performance increase you get for greater parallelism, and Amdal's Law is applicable to any system where you are interested in the effect of local improvements on the system globally. Amdal's Law highlights the effects of bottlenecks in a system. Contrary to Moore's Law that does not have any logical formula, the Amdal's Law does have a formula. There is a much more advanced formula out there, but this is simply a simplified version and the most famous that is out there. So the overall speed up of a system is calculated with the formula. Speed up equals 1 over 1 minus f plus f over SUF. So the f is the fraction of the time before the enhancement. And SUF is the speed up of that feature after enhancement. After all, we do want to increase the computer's performance, so Amdahl's law formula involves an enhancement in the system. So some examples of it is that when f is the 70% floating point, which remains like a 30% integer, and the SUF speed up factor is 3, plugging that into the equation, you'll see that the speed up is 1.875. And now, the other way to think about it is that when f is a 40% floating point, thus independent of the speed up factor, which I'll show you in another slide, the maximum speed up can never be more than 1.67. And now let's look at how it relates to computer architecture. So in order to see that, let's look at the definition of computer architecture. Well, it does refer to those attributes of a system visible to a programmer, or put in another way, those attributes that have a direct impact on the logical execution of a program. Now, looking in Moore's law, it all depends on all the transistors in the central processing unit hardware. In fact, there was even a Jeopardy question that I saw a few weeks ago focusing on Moore's law. And the correct answer was, what are transistors? Now for Amdahl's law, we look at also the CPU, but then there's the cache memory, the main storage, and the hard disk drive interaction with the system performance and parallelizing the subsystem. In including with that Amdahl's law, the time and effort best spent improving the system's performance are by those system components that can be improved in parallelizing part of the system while others remain the same. And this is an example of make the common case fast. And now we have come to find some profound consequences of Moore's law. With the advent of increasing speeds in a computer system, we have come to realize these 5 facts. Number 1, the cost of a chip has remained virtually unchanged during this period of rapid growth and density. This means that the cost of computer logic and memory circuitry has fallen at a dramatic rate. Number 2, because logic and memory elements are placed closer together on more densely packed chips, the electrical path length is shortened, increasing operating speed. Number 3, the computer becomes smaller, making it more convenient to place in a variety of environments. Number 4, there is a reduction in power requirements. And then number 5, the interconnections on the integrated circuit are much more reliable than solder connections. With more circuitry on each chip, there are fewer inter-chip connections. And as we look at this Amdahl's law for multiprocessors, we can learn that Amdahl's law helps us calculate a limit for how much any given level of parallelism could speed up a computation. According to this law, a problem that is only 50% parallelizable cannot attain better than a double the speed up time, no matter how many processors we throw at it. For a problem where 75% could be parallel, the maximum speed up is 4 times. For 90%, it's as large as 10 times. And if 95% can be parallel, speed up can be at most 20 times. Now, however, there are theoretical upper limits in practice that can be other constraints too. So as you can see in the figure, there's always a top limit for the speed up, no matter how many processors are available. Now, a follow-up to Amdahl's law called Gustafson's law helps us determine how much larger of a problem we can handle given more processors. Hooray! Parallel computing is here, so both Moore's law and Amdahl's law is still a work in progress. We are always learning something with each and every year of our lives, and computers must work simultaneously in order to achieve its best. So thank you for your time during my presentation. I would be happy to address any questions at this time.